A mixture containing 32 weight percent 1-propanol, 45.5 weight percent methanol, and the balanced water go through a process that produces two product streams. After analyzing the streams, one stream is found to contain 23.7 weight percent 1-propanol and 43 weight percent methanol. The second stream flows at a rate of 345 kilograms per hour. Draw a complete flowchart for the process, and what are the molar compositions of the second stream? Assume a basis of 1,000 kilograms per hour in the feed. So first we're going to start by defining the problem with a flow chart. We find going into the feed where there's 1,000 kilograms per hour, which is given to us in the problem, and then we have the weight percents of 1-propanol, methanol, and water. And our first stream, we are also given the weight percents, but not the rate. And then with the second stream, we have the rate, but we do not have the weight percent. So those are what we're going to find. So next we're going to collect information using what was given to us. Our assumptions show that this problem is continuous, steady state with no reactions, and they tell us there is a basis of 1,000 kilograms per hour in the feed. There are three unknowns, which I talked about before, the rate and the weight percents. And then we have three independent equations that relate the unknown variables. So now we're going to find the degrees of freedom using our unknowns and independent equations. We have three unknowns. Subtract that with three independent equations, we get 0. A degree of freedom equal to 0 means that the problem is solvable. We know the problem is solvable. We have our general balance equation. Input plus generation equals output plus consumption plus accumulation. Since it's a steady state, our accumulation equals 0. Since it's a non-reactive process, our generation and consumption are also 0. We're going to cross those three out, and we are left with input and output, so they equal each other.
We can see the flowchart we made earlier, as well as the formulas we will be using in order to find the m.1 and the weight percents of the 1-propanol, methanol, and water in the second stream. We have already converted each molecule's initial weight percent into a decimal and substituted them into their respective formulas. Since the input is equal to the output, m.I is equal to the sum of m.1 and m.2. Therefore, the formulas we will use to find the weight decimals of 1-propanol and methanol is m.I times the initial weight decimal of the molecule in question, set equal to m.1 times the weight decimal of the molecule in stream 1 plus m.2 times the weight decimal of the molecule in stream 2. For the weight decimal of water, we will use the formula m.I times the initial weight decimal of water, set equal to 1 minus x plus y, where x is the value we obtained from solving the 1-propanol balance formula, and y is the value we obtained from solving the methanol balance formula. Now we will use the formulas from the last slide to calculate the m.1 and the weight percents of each molecule in stream 2. We find that m.1 is equal to 655 kilograms per hour by substituting the m.I and m.2 values from the flowchart into the overall balance formula, then solving for m.1. Next we will substitute the values for m.I, m.1, and m.2 into the 1-propanol balance formula, and then solve for x, which comes out to 0.4776 or 47.76 weight percent. Then we substitute the m.dot values into the methanol balance formula and solve for y, which comes out to 0.5025 or 50.25%. Finally, we substitute the decimal values for x and y into the water balance formula and get a weight percent of 1.99. Now that we have the weight percents, we can find the molar composition of the second stream. First, we must assume that 100 grams of stream 2 contains 47.76 grams of 1-propanol, 50.25 grams of methanol, and 1.99 grams of water. We start by dividing 47.76 grams of 1-propanol by the 100 grams in stream 2 to find the amount of 1-propanol in 1 gram. Then we will convert that value to moles by dividing by the molar mass. Finally, we multiply by 345,000, which is the m.2 converted from kilograms to grams. We get 2,741.6 moles of 1-propanol in the stream. We use the same approach to solve for the amount of moles of methanol and water in stream 2, which come out to 5,410.8 and 381 moles respectively. Next, we add the 3 mole amounts up to find the total amount of moles, which is 8,533.4. Then, in order to find the mole percent of each molecule, we divide the amount of moles of each molecule by the total amount of moles. By doing this, we get 32.13 as the mole percentage of 1-propanol, 63.41 as the mole percentage of methanol, and 4.46 as the mole percentage of water.
To answer part A of the problem, we have the completed flowchart with all the unknowns filled in. As you can see, we have M1 filled in as 655 kilograms per hour. We've also found all the weight percentages for the unknowns in stream 2, being 47.76 weight percent for 1-propanol, 50.25 weight percent for methanol, and 1.99 weight percent for the unknown water. The answer for part B we found by taking the weight percentages from part A and converting them to molar percentages, therefore getting the molar composition of the second stream to be 32.13 molar percent of 1-propanol, 63.41 molar percent of methanol, and 4.46 molar percent water. Moving on to the last step of problem solving, to verify our answers for accuracy, we used Excel functions and tables calculating the molar percentages in stream 2. We plugged in our formulas to calculate the molar percentages, getting 32.12 for propanol 1, 63.40 for methanol, and 4.48 for water. Therefore, our answers make logical sense and are fairly accurate, reflecting only a 0.01 or 0.02 molar percent difference. Chemical processes have a real-world application in chemical plants and distillation processes. However, chemical processes happen all around us all the time, like using the washing machine. This specific problem has a real-world application in chemical plants, where gases are used and split into two streams that have different flow rates. In a real-world example, a chemical engineer would be used to calculate the percentage of each gas in each stream, as we have done in this example.